Hello, I am Justin Zuniga, and today I am presenting on the applications of mass spectrometry that are relevant to the field of polymer science. I will talk about some of the components of a mass spectrometer and define some important parameters related to polymers. We will also discuss the limitations with respect to other techniques for characterizing polymers, and finally we will explore the fragmentation patterns of different polymer systems and provide a brief introduction on how to interpret spectral data. I would like to point out that my sources relevant to the topic will be displayed on each slide. I would like to first define what mass spectrometry is. It is a powerful technique that determines the composition and the structure of the analyte. It does this by measuring the ion signal and the mass-to-charge ratio. The mass-to-charge ratio is essentially the molecular formula of the ion peak with respect to the charge. Now, there are four processes that make up the function of a mass spectrometer: ionization, separation, filtering of the ions, essentially is what that's referring to, detection, and the data acquisition. So now we're going to talk about mass ionization sources. So with mass spectrometry, there are two types of ionization sources or classifications. The first type of ionization is known as hard ionization, while the second is referred to as soft ionization. The difference between the two boils down to the degree of fragmentation. A soft ionization source will maintain the structural integrity of the molecular ion or the analyte of interest with minimal fragmentation. Hard ionization sources will analyze your molecular ion into many product ions or the fragments of your analyte. So just to give you an example of two hard ionization sources, we would have EI or CI, while MALDI and ESI are considered soft ionization sources. The two most commonly used sources to characterize polymers are ESI and MALDI. Now, there is something here that I think is really important to note with respect to ESI and MALDI. There is a major limitation of this technique. We have a hard time analyzing nonpolar samples from low molecular weight all the way up to high molecular weight. And that's going to be a topic of discussion over the next couple of slides. Now we will briefly talk about two important mass analyzers, the quadrupole and the time of flight. The quadrupole is composed of four parallel rods. One set is negative and the other set is positive. A DC and RF voltage is applied. The quadrupole functions as a scanning mass analyzer that uses the stability of the ions traveling through an oscillating electric field to separate ions that are based on their mass-to-charge ratio. The quad can provide quantitative and qualitative information. So in reference to the time of flight mass analyzer, TOF is classified as a non-scanning mass analyzer that will emit ions from the ionization source. The ions are accelerated through a tube. The velocity of the ions is converted to a mass-to-charge ratio or value. The TOF analyzer are great for acquiring full mass spectra and is also an excellent choice for quantitative and qualitative studies. In this table, the capabilities between the two mass analyzers are compared. The resolution and the mass accuracy for the quad improves when we start to utilize multiple quads together, so for triple quad. With respect to TOF, we see that when we change the structure of the time of flight tube, a similar increase in the capabilities is noted. So next we're going to really talk about understanding the mass spectrometer and some of the advantages and the limitations for polymer analysis. Polymer ionization is challenging for polymers because structurally polymers are large entangled macromolecules that are not easily ionizable. So we should recognize that not all polymers will ionize, and this may be due to the method parameters and other properties associated with the polymer. So when applying MS capabilities, we should understand how the different components as well as the solvent-polymer interactions work together to produce a given spectrum. One important feature to note regarding mass spectra of polymer systems is that the spectral data contains repetitive patterns with peak series that are spaced by the monomer unit. It is important to also recognize that there is no universal method that can be configured to analyze all applicable polymers. There are multiple applications that is great applying mass spectrometry to analyze polymers. So now, polymer scientists have really underutilized this potential to study polymeric systems through mass spectrometry. The increasing interest to capitalize on the advancement of MS capabilities for polymer science is certainly evident within the field. So for these reasons, polymer scientists should invest in MS technologies. MS offers a route for polymer scientists to develop methodologies for the characterization of synthetic polymers, biopolymers, and polymer biomolecule interfaces and conjugates. So in this slide, I really want to talk about the major applications of the selected polymer characterization techniques as a comparison to mass spectrometry, and really so that we can evaluate its feasibility in polymer science. GPC is the most commonly used technique to determine the polymer's molecular weight. The data acquisition process for collecting the data is based on the separation of the polymer's hydrodynamic volume rather than the polymer's actual molecular weight. So the end user is required to convert the raw data into a usable molecular weight scale. This conversion is based on the use of calibrating standards and analyzing the polymer samples under the same operating conditions. This method is based on relative proportionality, which means that this technique is prone to significant errors. As a comparison to mass spectrometry, we can also characterize the polymer's distribution properties. Using the molecular weight average calculations, we can do so with a high accuracy. One of the main differences or primary differences between mass spec and GPC is that the mass spec can measure the mass directly without having to convert the scale. NMR, X-ray diffraction, and mass spec, as you can see, have very similar applications for characterizing the polymer structure, but there are some variations that are important to note. NMR analysis can be utilized to determine the monomer sequence, reactivity ratios, and polymer microstructures. This would also be true for mass spectrometry. Which technique performs these tasks better will depend on polymer choice, instrument capabilities, such as the method detection limits and sensitivity, as well as other analytical constraints concerning the sample matrix, all important considerations that can be limiting for most colligative methods. It is important to note that NMR is not dependent on the sample condition, unlike mass spectrometry. For NMR, we can use a minimal sample volume. Sensitivity of the mass spec is actually much greater when compared to NMR. Mass spec analysis is dependent on the sample conditions, where consideration of the polymer's ability to ionize is critical. The ability for polymer ionization is dependent on the mode of polarization, the sample matrix such as the pH, and the ionization efficiency of the specific polymer. NMR analysis does not require these additional steps in the sample preparation process. Unlike mass spec, NMR can distinguish between a set of chiral polymers with the same molecular weight. For MS, separating enantiomers would require using a chiral column in the process. X-ray diffraction, which is a non-destructive method, is great for probing the surface and determining the polymer's degree of crystallinity. Mass spectrometry would not necessarily be a great choice for performing this type of analysis. All right, in this slide, I'm going to really talk about the sample preparation of polymer materials for MS analysis. So what's important to recognize is that by optimizing your sample conditions, you can obtain spectral data that is both accurate and reliable. It is important that we do acquire compatible polymer solvent blends. MALDI is the more commonly applied technique based on the ability to generate reproducible data for polymer systems and its ability to minimize multiply charged species, while ESI tends to fare better with biomolecular compounds. ESI does have difficulties with reproducibility due to the generation of multiply charged species. With ESI, there is a limit to the solvents selected and the range of solutions that can be analyzed. That is because not all solvents are ideal for ESI ionization. MALDI requires additional considerations for sample preparation in order to ionize certain polymers. A great example of this matrix effect is shown in the 4 spectral data. So different additives were mixed with polycaprolactam, and what we can see is that the polymer distribution profile was greatly affected depending on what type of additive that you use. If we take all this information together, the main idea is that there is a need in polymer science to develop new matrices that can be applicable to a broad class of polymers. This would enhance our capabilities to utilize mass spectrometry as a viable tool in polymer science. So I do want to point out something that's very important here. So when we look at the distribution profiles, we see that we don't achieve the results that we want. This is a great example. We like this broad, this Gaussian shape profile, and that's going to give us the most accurate information regarding our polymer system. All right, so in this slide, I want to talk about how we can acquire the ability to analyze nonpolar synthetic polymers utilizing ESI. So now, continuing with the discussion regarding the sample preparation process, we understand that not all polymers are ionizable by MALDI or ESI. What I liked about this study that these authors performed is that they make a very interesting point, indirectly at least, that ESI should be the more commonly used source to ionize polymers. Now, if you think about it, ESI enables a broad assessment of polar polymers, proteins, and other materials that solubilize in solvents that are most compatible with ESI. This is a very, very important distinction because we could minimize the sample preparation criteria to analyze a wide range of polymers without really having to utilize different ionization sources or using different matrix additives to help improve the ionization efficiency that we see with MALDI. Now, if we could modify the sample matrix in such a way that we could also analyze nonpolar polymers, we would essentially be one step closer to developing a universal method of ionization that would be applicable for all polymers. So at least that's the goal, and as you can see, much research is still needed in this area of polymer science. So to conclude from this study, the authors applied supercharging agents by chlorine attachment to perform their negative mode ionization. And what they found is that by incorporating supercharging agents into the solvent matrix, the ESI efficiency improved and was able to ionize the polymers that were basically currently inaccessible to ESI MS. Now, in this slide, I want to talk about polymer fragmentation patterns and the interpretation of spectral data. So, fragmentation is a term that is used to describe the process for generating characteristic ion peaks in a mass spectrum. The ions that are generated are considered the most stable form and they contribute to the observed pattern, that being the mass spectrum. The spectral lines provide us with structural information of the molecule. On a side note, the order and the connectivity of the polymer can also influence the observed pattern. This pattern will be primarily dependent on the functionality, such as the organic functional groups of the polymer, the ionization source, and the mode of ionization, that being, is it a negative or positive mode. There are other considerations such as the sample matrix and the method parameters that will influence the fragmentation pattern. So the polymer fragmentation mechanisms, they are critical for structural elucidation. Without going into too much detail, the fragmentation pattern does provide us with some guidelines to interpret the spectral data. I guess the most important thing is that there is a correlation between the ion stability and the abundance of that ion within the spectrum. An ion that is most stable will have a greater abundance. It is best to think of the spectra as a puzzle, where you as the interpreter can take a piecewise approach to assemble the molecular structure to determine the structure of your molecular ion or your analyte in the sample. So from any given polymer, we should be able to predict its fragmentation pattern or the resulting spectrum based on the most abundant peaks expected to appear. One approach is to really study the organic reaction mechanisms for each polymer and predict which bonds could break when subjected to an ionization source. So, of course, there are some basic ionization mechanisms that do occur. However, that involves a lot of chemistry and is an area of ongoing research that really is needed in order to improve our understanding of how compounds ionize. So, here are a couple examples demonstrating the fragmentation patterns of various structures. And there's a couple things that I want you to recognize here. So this is the ion, molecular ion. This is the heaviest ion for this spectrum. And when we go from this point to this point, you'll notice that there is a slight change in the structure. The difference between these two spectral lines is the molecular mass that was lost during fragmentation. And if we go from this peak to this peak, we actually see this entire arm just disappears. The difference between the spectral lines, again, is going to equal that molecular formula that was lost during fragmentation. And, and that's just a simple way to kind of understand what is happening. There is mechanisms that we can apply to really understand the process. And again, we could do the same thing with this spectrum, and we then notice something else is happening. We see that there is rearrangements of the double bonds. So that's something else to keep in mind when evaluating the fragmentation patterns. This is a monomer, and the difference between this spectral line and this spectral line is really the molecular weight of the monomer unit for that polymer. All right, so in this slide, I want to talk about the fragmentation pattern of polyethylene glycol in the negative and the positive mode, and to look at the differences in their fragmentation patterns. So the positive mode fragmentation pattern of polyethylene glycol is well known. And in this study, the authors, they wanted to design an investigation that allowed for them to study the negative ion ESI fragmentation reactions of the deprotonated polyethylene glycol, starting with the ethylene glycol polymer and making it a function of oligomer length. So it's important that we first understand, what is this B notation here? Well, the B notation is really used to depict the fragment size as a function of the number of monomer units. So what we see in the negative mode is that the polymer size also can influence the spectral pattern. So polymers that varied in length by 1 monomer unit were each analyzed. And every time we saw alternating B fragments in terms of the intensity within the spectrum. So if N was even for a precursor polyethylene glycol fragment, the even number B fragments would also have a greater relative abundance or intensity when compared to the odd number. And this alternated throughout. In the positive mode, we do not see that pattern at all. If we notice with the negative mode, it produces an ion here. And these two reactions, and even this reaction, structurally, they don't really change. The N group, or the site where deprotonation occurs, is consistent. And if we take symmetry into account and we flip the polymer and we use the other side, it's still going to attribute to the same feature. I guess the major observation though is that you do see fragments yielding the loss of the monomer unit. You see the elimination of the hydride, as well as loss of water. And you'll see those in different combinations. All right, so to kind of conclude like the major highlights of this presentation regarding polymer analysis by mass spectrometry, it's really important to understand what information it is that you seek and what is the best approach to obtain that information. So mass spectrometry is definitely a complicated process, and there are certainly many limitations that can complicate the process even more with respect to like the sample preparation, and then if we can really understand the challenges, we can begin to solve some of these critical issues that relates to like the polymer science, and we can then start to improve our capabilities to analyze a broader range of polymers, and that's really what the goal here is. The polymer solvent matrix effects is going to be like one area for like continued research, and really how can we build on the information to improve the ability to ionize a broader range of the polymers, and if we can, that will certainly be advantageous. One of the primary objectives of this presentation was to evaluate polymer fragmentation patterns, and there are three important things to remember. A mass spectrum for any polymer, now that's assuming that the polymer solvent matrix is not an issue, will produce a repetitive pattern in the shape of a distribution profile. Now, as we can see this with the ethylene glycol in red, and then blue with the changes of the end group to that of an ethylene fluorobenzene derivative. The mass spectrum, which is the other point, the mass spectrum is the fingerprint of a molecule where you can piece together like the different fragments to really determine the identification or the structure of your analyte or polymer. And finally, a mass spectra contains hidden data, and that we can use to connect the pieces. Now, the differences between two spectral lines is the structure component that connects the fragments, and we put it together and we really begin to understand the structure of the polymers, and that's one of the things that I think is so great about mass spectrometry. And on top of that, we really are able to extrapolate a lot of information. We can determine end groups, we can find the polymer impurities for processing operations, to like researching synthetic polymers, to the development of like new applications. That even really includes like drug discovery initiatives. So like as an example, if we considered proteins and peptides that are involved in the viral replication of HIV, and then we were to subject these proteins or peptides to a mass spectrum or mass spec, we would actually be able to determine its fragmentation pattern. So by interpreting the fragmentation pattern of those proteins, we would then maybe possibly identify potential areas where the amino acid sequence could be targeted with the use of drug inhibitors, so that we could actually inhibit its replication from occurring. So at the end of the day, there's still a lot of need to expand our research capabilities, and I certainly believe that mass spectrometry can help us to advance the field of polymer science and really to discover how to synthesize new materials and to learn more about like the underlying mechanisms that influences the polymer properties.